So how do solutions form? Well, in the liquid, in the solvent, I say liquid, we'll mostly talk about solids dissolved in liquids. In the solvent, and here we have an example of sodium chloride dissolved in water, there are forces of attraction between the solvent molecules. There's dispersion forces, dipole-dipole forces, and hydrogen bonds between water molecules. So those are pretty strong attractive forces. We call that a solvent-solvent attraction. Between sodium ion and chloride ion, we have ionic bonds, and those are really strong. That's a solute-solute attraction. And then we have attraction between the solute particles and the solvent particles. So because water is polar, the negative end of the water molecule is attracted to the positive ion, the cation. And the positive end of the water molecule is attracted to the anion. And so we have these competing forces. And if the forces of attraction between the solvent and the solute are strong enough, then it will dissolve. Not all ionic compounds are soluble in water. Sodium chloride is, but calcium carbonate is not. In calcium carbonate, the attraction between the solute particles is too strong. And they would rather stay clumped together and they're solid in the bottom of the beaker than dissolve and spread around. So here's an illustration of how sodium chloride dissolves in water. So here we've got an illustration of a sodium chloride lump, maybe, crystal. It's an ionic compound. It's just ions, back to back, all the way through. It's really, you could think of it as one giant molecule. And the water molecules come up to it, and the positive ends, the hydrogen ends of the water molecules are attracted to these negative ions because the hydrogen end is slightly positive. And so they will come up and surround it and make it comfortable. Because in order for this chloride to leave the attraction that it has for these sodium ions, that force of attraction has to be replaced by something. And one water molecule is not going to do it, but a bunch of water molecules surrounding it. And so in my, crazy chemistry world, this is, you've got these people that came and they were in a group together. And they're like, we like each other, we know each other, we don't want to go mingle with other people. And the water comes up and it's just really friendly and says, oh, come out and play, you'll be fine, and talks it away from the group, right? Water can also talk the sodium ion away because water just turns its back and it's the other charge. And so it can make both cations and anions feel comfortable, okay? It replaces those forces of attraction. When an ionic solute, like sodium chloride, dissolves in water, the ions separate and they disperse throughout the solution. Each of these ions is surrounded by water molecules and is attracted to the water molecules around it. And those are kind of like escorts, and they allow it to move freely throughout the whole solution. And so we get a homogeneous mixture. It's the same throughout. You'll have the same. It'll be just as salty at the top as it is at the bottom. Now, of course, you can't dissolve an infinite amount of solute in a beaker of water. Eventually, it stops dissolving, right? You could try this at home. Take a little glass of water and add salt and stir it, and it'll dissolve, and add some more and stir it. Eventually, you'll get to a point where you add more salt, and no matter how much you stir, it will not dissolve anymore because the water is full of the solute. It just can't handle anymore. There's no more free escorts to come and usher these guys around and you make them feel comfortable. And so when you've reached that limit, that's the solubility. Solubility is usually defined as the amount of a compound, the solute, usually in grams, that dissolves in a certain amount of liquid. And so typically that'll be grams per 100 grams of water. So for example, solubility of sodium chloride at 25 degrees Celsius is 36 grams of sodium chloride per 100 grams of water. So if you have 100 grams of water, you could dissolve 36 grams of sodium chloride in it. If you added one more gram, that extra gram of sodium chloride would not dissolve. It would just fall to the bottom of the beaker and sit there. When you are at that solubility, we could say that's a saturated solution. because the water has accepted and encompassed as much of the solute as it possibly can. It's full. It's saturated. So in a saturated solution, you have the maximum amount of solute under those conditions. If you add more, it doesn't dissolve. Now we specify the temperature here because temperature does have an effect on the solubility. So what if it's unsaturated? An unsaturated solution has less than that maximum amount. And so you could put more in and it would dissolve. And then we have supersaturated solutions. A supersaturated solution is one that holds more than the normal amount, the normal maximum. This is an unstable situation, and that extra solute will normally precipitate out of solution. So how could you put more in than is possible? How can it hold more than it can hold? Well, there's a couple of different ways that this can happen. One is if you heat the solution, the solubility increases. So if you make a saturated solution at a higher temperature and then you allow it to cool slowly and carefully, it may kind of not notice that it's gotten cooler and it shouldn't be soluble anymore. Okay, that's, me personifying atoms and molecules again. But it makes more sense, doesn't it? It will, like sodium acetate, will do this. And if you remind me in lab, I'll do a demonstration for you and show it to you. It's really kind of cool. So you've got this clear solution that's super saturated because it was saturated at a higher temperature and you've allowed it to cool down. And then you disturb it by putting one tiny little crystal in it, and all that excess precipitates out within a matter of seconds. It's really pretty amazing. Another way that can happen is with pressure. So you open a soda can. The soda can has pressure of carbon dioxide in it. When you suddenly release that, you can have a supersaturated solution form because the carbon dioxide that's dissolved in the water has not had a chance to come out yet. And so there's actually more dissolved in there than there should be. So supersaturated solutions are kind of weird and kind of fun. Here's a picture of that sodium acetate. So this was made, this was a saturated solution at a higher temperature and allowed to cool down. And then you add just one crystal and it starts to crystallize, and you can see the crystals forming, and then it becomes almost solid, full of crystals. And if you get the proportions just right, when it's done, you can take the beaker and turn it over and no water comes out. It's really fun. Solubility rules, we learned about those earlier. Those give us a qualitative description of the solubility of ionic compounds. Some things like calcium carbonate are insoluble, and we mentioned this a few minutes ago, because the attraction between the ions is greater than the attraction between the solvent and the solute molecules. So not all ionic compounds are soluble. And understanding the energetics and the reasons behind that is very complicated. And so we just go with that list, those rules of solubility. But molecular solids can also be soluble in water. Sugar dissolves in water. It's not ionic. Table sugar has a formula C12H22O11. There's no metals in there. It's a covalent molecular compound. So molecular compounds can dissolve, but again, the polarity is going to affect it. So dissolving in water, it needs to be a polar molecule. A nonpolar molecule, like lard or vegetable shortening, cooking oil, gasoline, anything like that that's nonpolar is not going to dissolve in the water. So when ionic compounds dissolve, they form electrolytes. So an electrolyte solution is a solution that contains charged particles, contains dissolved ions. So you put sodium chloride in water, and we already talked about this, and it separates into sodium ions and chloride ions. You have charged ions in here. Electric current is a flow of electrons. And in a solution, in order for the current to flow, you have to have some charged particles that can carry those electrons. Kind of like, ferrying them across the river or whatever. When you dissolve an a molecular compound like sugar, it does not form ions, and we say that this is a non-electrolyte solution. Electrolyte solutions will conduct electricity, Non-electrolyte solutions do not conduct electricity. They don't have any charged particles to carry the current. In general, for solids in water, the solubility will increase with increasing temperature. Let's look at this graph. So here on the y-axis is solubility, measured in grams of solute dissolved in 100 grams of water. So like right here at 0 degrees Celsius for sodium nitrate, looks like about 72, 73 grams of sodium nitrate will dissolve in 100 grams of water at the freezing point of water. And as you increase the temperature, the solubility increases. So here at 30 degrees, you could dissolve about 95. So some of these have a very strong temperature dependence, like potassium nitrate, just shoots up as the temperature goes up. And some of them, like sodium chloride, the solubility is relatively constant. You go from water at the freezing point to water at the boiling point, and the solubility has changed, maybe 7 grams out of 35 or so? It doesn't change much at all. But in general, as you increase the temperature, you increase the solubility. The solubility, however many grams per 100 grams, that's the amount needed to make a saturated solution. That's the limit. Sometimes we call it the solubility limit. One way to purify solids is by recrystallizing them. And so what you do is you take the solid, it has to be soluble in the solvent you're going to use. You take the solid that you want to purify and you dissolve it in a solvent at an elevated temperature. So you make a fairly saturated solution of that at an elevated temperature, and then you allow it to cool down slowly. And as that happens, that solute will precipitate out. When it precipitates out slowly, and the crystals form slowly, they tend to exclude impurities. When it precipitates quickly, it's common for impurities to get trapped inside. So when you do it slowly, the crystalline structure tends to reject impurities, and it gets you a purer solid, and they tend to have better crystal structure too. And this idea can be used to make rock candy. So if you take table sugar and make a saturated solution at an elevated temperature, how do you do that? Well, you put some hot water in a container, and you add sugar till no more sugar dissolves. So very hot water full of sugar. And then you dangle a string in that, and you let it cool down. And as it cools down, it can take several days to form the rock candy, but the sugar will crystallize onto that string, and you'll get these beautiful crystals of sugar. And that's how they make rock candy.